Imagine standing under the night sky, gazing up at a universe that seems infinite and unchanging. But what if I told you that somewhere out there, particles are hurtling through space with energies so unimaginably high they defy everything we know about physics? These aren't just any cosmic visitors, they're ultra-high-energy cosmic rays, and they carry mysteries that have left scientists scratching their heads for decades. Some of these particles pack more energy than a baseball thrown at 90 miles per hour, but they're smaller than an atom. How is that even possible? And where could they possibly come from? The universe, it seems, still has secrets it's not ready to reveal. Now, picture this: 30 of these cosmic rays have been detected over the years, each one so powerful that their origins remain a complete enigma. These aren't just random space debris, they're cosmic anomalies that challenge the very laws of physics as we understand them. According to our best theories, particles like these shouldn't even reach Earth. The energy they carry should dissipate long before getting here, lost in the vast emptiness of space. Yet here they are, defying logic, leaving even the brightest minds in astronomy and physics puzzled. What cosmic engines could possibly accelerate particles to such incredible speeds? Are we looking at the aftermath of a supermassive black hole's fury, or could there be something even more exotic at play? This is more than just a scientific curiosity, it's a mystery that could rewrite our understanding of the universe. These ultra-high-energy cosmic rays might hold clues to phenomena we've never even dreamed of, lurking in the darkest corners of space. And that's what we're diving into today. From the mind-boggling challenges of detecting these particles to the wild theories about their origins, we're about to explore one of the most fascinating unsolved puzzles in modern astrophysics. So buckle up, because this journey will take us to the edge of known science and beyond, where the answers we find might be just as strange as the questions we're asking. One October night in 1991, a cosmic bullet tore through Earth's atmosphere with so much energy it left physicists speechless. Dubbed the "oh my God" particle, this single proton smaller than an atom packed the punch of a baseball smacking into your face at 60 miles per hour. But how? Its energy level was a staggering 320 exa-electron volts. To put that in perspective, it carried millions of times more energy than anything our most powerful particle colliders can produce. Even the Large Hadron Collider, humanity's most advanced atom smasher, can't come close to replicating such a monstrous force naturally, the real shocker. According to everything we know, this particle shouldn't exist. At such extreme energies, cosmic rays should lose steam long before reaching Earth, their energy sapped by interactions with the cosmic microwave background, the faint afterglow of the Big Bang itself. Yet the "oh my God" particle laughed at those rules. It arrived intact, as if it had cheated the universe's own friction. So where did it come from? The leading theories are as wild as the particle itself. Some suggest it was hurled our way by a supermassive black hole's relativistic jet, a cosmic cannon capable of accelerating matter to near light speeds. Others speculate it might be the fallout of a hypernova, an explosion so violent it dwarfs even supernova. But here's the twist: no known source within hundreds of millions of light years seems powerful enough to produce it. If it came from a distant galaxy, how did it survive the journey without losing energy? And if it came from somewhere closer, why can't we pinpoint the culprit in our cosmic neighborhood? 3 decades later, the "oh my God" particle remains a tantalizing outlier, a cosmic ghost that refuses to reveal its secrets. It's not just a scientific curiosity, it's a glaring hole in our understanding of the universe's most extreme physics. And until we find another like it or finally trace its origins, it stands as a humbling reminder. Sometimes the universe sends us a message so baffling, all we can say is "oh my God." The mystery of the "oh my God" particle isn't just about its impossible energy, it's about the cosmic powerhouse that launched it. Scientists have spent decades chasing clues, and the leading theories sound like something straight out of science fiction. Take supermassive black holes, for example. At the hearts of galaxies like M87, these monsters spin with such ferocity that they can shoot jets of plasma across the universe at nearly light speed. Could one of these cosmic particle accelerators have hurled the oh my god particle our way? The math suggests it's possible, but here's the catch. Even the most energetic black hole jets we've observed don't quite match the particle's ridiculous energy level. It's like comparing a firecracker to a nuclear bomb. Then there's the idea of active galactic nuclei galaxies with cores so bright they outshine every star around them. These cosmic lighthouses are powered by insatiable black holes surrounded by disks of superheated gas. As material spirals inward, it could theoretically fling particles to extreme energies. But again, we hit a wall. The nearest active galactic nucleus is millions of light years away, and over that distance, the particle should have bled energy like a marathon runner hitting a wall. Yet it arrived fresh as a daisy, as if it had some unseen cosmic cheat code. Some researchers have turned to even wilder explanations. What if the particle wasn't born in a black hole or a star, but from something far stranger like a cosmic string? These hypothetical defects in space-time, leftovers from the Big Bang, could theoretically snap like rubber bands, releasing insane bursts of energy. Or maybe it's a whisper from the dark side of the universe, a particle born from decaying dark matter, a substance we know almost nothing about. These ideas push the boundaries of known physics, but that's the problem. They're so speculative, we have no way to test them yet. The truth is, none of these theories fully explain the oh my god particle. Each one has a flaw, a gap in the math, a missing piece of evidence. It's as if the universe handed us a jigsaw puzzle with half the pieces hidden. But that's what makes this mystery so thrilling. Every time we think we've nailed it down, the particle slips through our fingers, reminding us how much we still don't understand. It's not just a scientific challenge, it's a cosmic wake-up call. The universe is stranger, fiercer, and more mysterious than we ever imagined, and the oh my god particle is just the beginning. The northern sky holds a secret, an invisible bullseye that's been catching ultra-high energy cosmic rays like cosmic moths drawn to a flame. In 2008, the Telescope Array project in Utah spotted something bizarre. A dense cluster of these extreme particles, all hailing from the same patch of space near the constellation Ursa Major. Statistically, the odds of this happening by pure chance are less than 1 in 10,000. It's like rolling a die and getting 6 sixes in a row. Not impossible, but so unlikely it demands an explanation. This isn't just a random scattering. The hotspot spans a region about 20 degrees across roughly 40 times the width of the full moon, and it's defied every attempt to find a visible source. No supermassive black holes, no hyperactive galaxies, not even a whisper of gamma-ray bursts. It's as if something invisible is lurking there, a cosmic sniper silently firing these particles across the universe. One theory points to exotic dark matter structures, massive, unseen clumps of matter whose gravity could funnel and accelerate particles toward Earth. Another idea suggests a local enhancement of the galactic magnetic field, bending cosmic rays into this eerie concentration like a lens focusing light. But here's the kicker. If magnetic fields are redirecting these particles, why don't we see similar hotspots elsewhere? The universe should be littered with them, yet this one stands alone, a cosmic anomaly with no obvious siblings. The Telescope Array hotspot forces us to confront a humbling truth. Our cosmic neighborhood might be weirder than we ever imagined. It's a reminder that even in an era of space telescopes and quantum physics, the universe still has cards it hasn't shown us. And until we uncover what's hidden in that dark patch of sky, this hotspot remains one of astronomy's most tantalizing unsolved puzzles, a beacon of mystery in the vast, silent dark. Somewhere out there in the vast emptiness of space, there might be an answer to our cosmic ray mystery hiding in the last place we'd think to look, a place where there's almost nothing at all. Scientists call these regions cosmic voids, enormous bubbles of near-perfect nothingness stretching millions of light-years across. Most would assume that without matter, these voids would be dead zones, unable to produce anything, let alone the most energetic particles in the universe. But that's exactly why they're so intriguing. Here's the twist: the emptiness itself might be the key. In a universe crowded with galaxies, stars, and magnetic fields, ultra-high-energy cosmic rays constantly collide with background particles, losing energy over time like a speeding car hitting resistance. But in a void where matter is almost non-existent, a particle could theoretically race through unimpeded, building up insane speeds without anything to slow it down. It's like running a sprint in zero gravity, no wind resistance, no friction, just pure acceleration. The problem: even if voids act as cosmic particle highways, we still don't know what's launching these particles in the first place. Some theorists suggest that shockwaves from rare, ancient galaxy collisions at the edges of voids could serve as invisible particle cannons, hurling matter into the void where it gains speed over unfathomable distances. Others propose that voids might amplify mysterious dark energy effects, twisting spacetime in ways we don't yet understand. But here's the catch: if voids are the source, why aren't we seeing more cosmic rays coming from them? The signals we've detected seem too sparse to fit neatly into the theory. This is where magnetic fields come crashing into the debate. The universe isn't just a static backdrop. It's threaded with invisible magnetic forces that can bend and redirect cosmic rays like a cosmic pinball machine. Some researchers argue that what we're seeing isn't a void's pristine acceleration at work, but the result of these magnetic fields funneling particles from multiple sources into deceptive clusters. Imagine throwing confetti into a fan. Even if the pieces came from different directions, the airflow could make them all land in the same spot. So which is it? Are voids the silent accelerators we've been missing, or are magnetic fields playing tricks on our observations? The truth might lie somewhere in between. Voids could provide the perfect conditions for particles to build energy, while magnetic fields act as cosmic lenses, warping their paths just enough to confuse us. Until we can map these invisible forces in greater detail, or catch more of these extreme cosmic rays in the act, the void hypothesis remains one of astronomy's most tantalizing maybes, an answer that's still just out of reach, hidden in the emptiest places imaginable. In the quiet desert of Utah in 1993, a cosmic enigma streaked through the atmosphere with a force that rewrote the rules, and it was caught by something called the fly's eye. This bizarrely named detector, a grid of mirrors designed to catch the faint glow of cosmic rays hitting the air, recorded a particle slamming into Earth with an energy of 200 exa-electron volts. That's a number so large it barely makes sense. Imagine a single atom carrying the punch of a major league fastball, but the real shock wasn't just its energy. It was where it seemed to come from. Most cosmic rays follow predictable paths, their origins tracing back to violent events like supernova or active galaxies. But the fly's eye particle arrived from a direction that left scientists stumped. Its trajectory pointed to a patch of space with no known cosmic powerhouses, no black holes, no star-forming regions, not even a whisper of gamma radiation. It was like tracking a bullet back to an empty firing range. Here's where things get even stranger. Based on our understanding of galactic and extragalactic magnetic fields, a particle this powerful should have been twisted and redirected during its journey, making its exact origin impossible to pinpoint. But the fly's eye event's path was suspiciously straight, as if it had slipped through the universe's usual obstacles untouched. Some researchers suggest this could mean it came from much closer than expected, perhaps from within our own galactic neighborhood. But if that's true, why haven't we found the source? Others wonder if we're dealing with something far more exotic. Could this particle have been flung our way by a yet undiscovered astrophysical phenomenon, a cosmic accelerator hiding in plain sight? Or worse, does its very existence hint at gaps in our fundamental understanding of how particles interact with magnetic fields? The fly's eye event doesn't just defy explanations, it taunts us with possibilities we can't yet prove. Decades later, this detection remains a thorn in the side of cosmic ray research. It's a reminder that for every rule we think the universe follows, there's an exception hurtling toward us at the speed of light, daring us to figure it out. Until we do, the fly's eye particle stands as proof that sometimes the most profound mysteries come from the emptiest corners of the sky. The cosmic ray we're calling the galactic plane paradox doesn't just defy expectations, it mocks them. When ultra-high-energy particles streak toward Earth, scientists expect them to follow the Milky Way's crowded galactic plane, where most cosmic accelerators like supernova remnants and pulsars reside. But this one took a detour, arriving from a direction that skirts our galaxy's dense core like a cosmic trespasser sneaking in through the back door. Magnetic fields should be the obvious culprit here. Our galaxy is laced with invisible lines of force that twist and redirect charged particles like cosmic pinballs. The stronger the field, the more a particle's path gets bent, and the Milky Way's plane has some of the most intense magnetic landscapes in our neighborhood. So when a high-energy cosmic ray avoids that region entirely, it's like watching a paper airplane fly straight through a hurricane without so much as a wobble. Here's where the math gets messy. For this particle to ignore the galactic plane so completely, either our understanding of galactic magnetism is fundamentally flawed, or this cosmic ray has properties we've never seen before. Some models suggest particles with extreme rigidity resisting magnetic deflection like a freight train plowing through fog, but even those should show some curvature in their path. The fact that we don't see any hints at something far stranger, perhaps this particle wasn't just passing through our galaxy's magnetic fields, but slipping past them entirely. One radical theory proposes these cosmic rays might be neutral particles like neutrons or hypothetical dark matter, candidates that don't interact with magnetic fields at all. But neutrons decay too quickly to travel interstellar distances, and dark matter remains. Well, dark, another possibility. The particle's journey didn't start in some distant galaxy, but right here in the Milky Way's sparse halo, where magnetic fields are weaker and paths straighter. Yet if that's true, we're left puzzling over what kind of local cosmic engine could possibly produce such outrageous energies without leaving any other trace. The paradox cuts deeper than just one particle's path. If ultra-high-energy cosmic rays routinely avoid the galactic plane, it challenges decades of assumptions about how the universe accelerates matter. Are we missing entire categories of cosmic accelerators lurking in the voids between galaxies? Could magnetic fields be structured in ways our current maps don't capture? Every detection like this doesn't just add to the mystery. It peels back another layer, revealing how much we still don't understand about the invisible forces sculpting our universe. Deep in the mountains of Japan, an array of detectors sprawled across the landscape like a scientific spiderweb waiting. The Akino Giant Air Shower Array, or AGOSA, wasn't just another cosmic ray observatory. It was a precision instrument designed to catch the faint whispers of particles screaming in from deep space. And what it found between 1984 and 2003 would shake up cosmic ray research forever. AGOSA detected something bizarre, a series of ultra-high-energy cosmic rays that seemed to come from everywhere at once. Unlike other cosmic messengers, which often cluster around known astrophysical powerhouses, these particles were spread evenly across the sky in what scientists call an isotropic distribution. Imagine throwing darts blindfolded and hitting every single section of the board equally. That's how perfectly random their arrival directions were. This uniformity is more than just odd. It's a direct challenge to everything we thought we knew about cosmic accelerators. If these ultra-high-energy particles came from identifiable sources like active galaxies or black hole jets, we'd expect them to arrive in clumps, pointing back to their violent birthplaces. Instead, Auger data showed no patterns, no preferred directions, just a cosmic shotgun blast of particles with no address labels. Theories scrambled to explain it. Some suggested these particles might be coming from much closer than we thought, trapped and scattered by the Milky Way's own magnetic fields until their origins were completely scrambled. Others proposed that they could be the remnants of decaying super-heavy dark matter particles, raining down uniformly from all directions, but the most unsettling possibility. That we're missing something fundamental about how the universe accelerates matter to such extreme energies. What makes Auger's findings so gripping is the sheer scale of the mystery. These weren't just one or two oddballs, they were part of a consistent pattern that defied explanation. And with no visible sources to blame, the question lingers: is the universe hiding a network of invisible particle accelerators, or are we staring at the fingerprints of physics we don't yet understand? For now, Auger anomalies remain a cosmic Rorschach test, a blank sky that might hold answers we're not yet equipped to see. Every time we think we've mapped the universe's most violent engines, discoveries like these remind us the cosmos still has cards it hasn't shown us. And until we crack the code of their isotropic spread, these particles will keep haunting the edges of our understanding, whispering secrets we can't quite decipher. Physicists once thought they'd found the universe's ultimate speed limit for cosmic rays, a boundary so absolute that nothing should cross it. Meet the UHECR cutoff, named after the three scientists who calculated it back in 1966. Their math was elegant and airtight. Any proton zipping through space with energy beyond 5 × 10⁻¹9 electron volts should hit an invisible wall. Not a physical barrier, but a brutal reality of cosmic friction. At those insane energies, particles inevitably smash into the faint afterglow of the Big Bang, photons left over from the universe's fiery infancy. These collisions should bleed cosmic rays dry, stripping them of energy over long distances like a marathon runner sinking into quicksand. Yet here's the cosmic curveball. Multiple ultra-high energy particles have crashed through that theoretical limit like it wasn't even there. It's as if someone fired a bullet through a brick wall, only to find it undamaged on the other side. The implications are staggering. Either these particles didn't travel far, meaning there's an unknown powerhouse lurking shockingly close to Earth, or our understanding of particle physics is missing a crucial chapter. Let's break down why both possibilities are mind-bending. If these cosmic rays are local, we're talking about an accelerator within roughly 150 million light-years, cosmic spitting distance. But our most detailed sky surveys show nothing in those regions remotely capable of such violence. No hyperactive galaxies, no colliding galaxy clusters, not even the faintest blip of gamma rays. It's like hearing thunder and seeing clear blue skies. The alternative: these particles crossed intergalactic space unimpeded, laughing off the UHECR cutoff as if the laws of physics took a coffee break. Some theorists suggest exotic quantum effects might let high-energy protons tunnel through the cosmic microwave background like ghosts passing through walls. Others propose radically new particle behaviors at extreme energies, perhaps evidence of extra dimensions or undiscovered forces, the most unsettling part. This isn't just one rogue particle breaking the rules. Multiple detections across decades confirm the pattern. The UHECR cutoff isn't just being nudged, it's being body slammed by reality. Every time one of these cosmic outlaws streaks through our atmosphere, it forces us to confront an uncomfortable truth. The universe might play by rules we haven't even imagined yet. Stretching across 3,000 square kilometers of Argentinian prairie, the Pierre Auger Observatory is one of the most ambitious cosmic ray hunters ever built. Its 1,600 water tanks and 24 fluorescence detectors form a sprawling net, waiting to catch the faint afterglow of particles smashing into Earth's atmosphere at nearly light speed. What it's found since 2004 has rewritten the cosmic ray playbook, but not without leaving glaring questions in its wake. The observatory's crown jewels are ultra-high-energy cosmic rays eclipsing 100 exa-electron volts, energy so extreme they make the oh my god particle look almost mundane. Unlike earlier detections that seem to come from nowhere, these particles show a tantalizing pattern. Their arrival directions weakly align with nearby active galaxies, specifically a class called starburst galaxies and those harboring hungry supermassive black holes. For the first time, it seemed we might finally have cosmic fingerprints leading back to the killers, but here's where the plot thickens. While the correlation exists, it's messy. Only about 60% of these ultra-high-energy rays point back to plausible sources, leaving the rest adrift in the cosmic void. Even more puzzling, the galaxies they do trace to are relatively close, within 300 million light-years, yet the particles show no sign of the energy loss they should have suffered along the way. It's as if these cosmic bullets traveled through a vacuum, untouched by the very forces that should have slowed them down. One leading theory suggests these galaxies act as cosmic lighthouses, their central black holes firing intermittent jets of particles like a sporadically triggered cannon. If the jets happen to point directly at Earth during a burst, we might catch a fleeting glimpse of their highest energy output. But this raises another problem. If these galaxies are indeed the source, why don't all their cosmic rays arrive with matching energies? Some show up weakened as expected, while others barrel through with undiminished fury. Another puzzle lies in the Milky Way's magnetic field. While it's not strong enough to redirect these particles completely, even subtle deflections over intergalactic distances should blur their trajectories, making precise source matching nearly impossible. Yet the Auger data shows clumps that are just a bit too sharp, hinting that something, perhaps unknown magnetic structures between galaxies, might be funneling these particles in ways we don't yet understand. The most unsettling possibility, that we're seeing two separate populations of cosmic rays mixed together, some from identifiable galaxies, others from something far stranger. Perhaps dark matter annihilations, hypothetical cosmic strings, or even flaws in our understanding of particle physics itself. The Auger data doesn't just hint at answers, it screams that our cosmic map is still missing entire territories. For now, the observatory keeps watching, its tanks and detectors poised for the next ultra-high-energy messenger. Each new detection could tilt the scales toward one theory or another, or scrap them all entirely. Until then, these mystery rays stand as both a clue and a taunt, reminding us that even when the universe gives us a trail to follow, the path might lead somewhere we never expected. Centaurus is the kind of cosmic rebel that refuses to be ignored. Lurking just 12 million light-years away, practically next door in galactic terms, this peculiar galaxy blasts powerful radio jets across the universe, fueled by a supermassive black hole 55 million times heavier than our Sun. For years, scientists have eyed it as a prime suspect in the ultra-high-energy cosmic ray mystery. After all, if anything nearby has the raw power to hurl particles at near light speeds, it's this monster. But does the evidence hold up, or are we seeing cosmic shadows where we want answers? The case for Centaurus starts with proximity. Unlike distant galaxies whose particles should lose energy crossing vast intergalactic voids, this one's practically in our backyard. Its jets, stretching over 1 million light-years, act like a natural particle accelerator, twisting magnetic fields that could theoretically slingshot protons to extreme energies. Even more compelling, the Pierre Auger Observatory's data shows a slight but noticeable clustering of cosmic rays from Centaurus A's general direction, too much to dismiss as pure chance. But here's where the skepticism kicks in. While some ultra-high-energy particles align roughly with Centaurus A's position, the correlation isn't perfect. Many arrive from slightly off angle, as if the galaxy's jets are spraying cosmic shrapnel in unpredictable directions. Worse, the highest energy detections don't match the expected energy loss patterns for particles traveling such a short distance. If Centaurus is the culprit, why don't all its cosmic rays hit us with uniform intensity? Some theorists argue that the galaxy's turbulent magnetic fields could be scrambling particle paths, deflecting them just enough to blur their origins. Others suggest we might be seeing secondary effects particles boosted by shock waves in Centaurus A's surrounding gas clouds rather than launched directly by the black hole. But the most tantalizing possibility, that we're witnessing something far rarer, a temporary surge in the galaxy's activity, a cosmic storm that briefly revved up its particle cannons to unprecedented levels. The debate rages because Centaurus represents more than just a single suspect. It's a test case for whether any active galaxy can explain these extreme cosmic rays. If even our closest, most obvious candidate leaves room for doubt, what does that mean for more distant sources? Every detection that almost fits pushes us closer to an uncomfortable truth. The universe might be forging these particles in ways we haven't imagined, in places we haven't thought to look. Until we catch Centaurus in the act, or rule it out for good, it remains both our best lead and a glaring reminder of how much we still don't know. In the pitch-black skies above Utah's desert, the high-resolution Fly's Eye detector, high-res for short, caught a cosmic ray unlike any other. Clocking in at 160 exaelectronvolts, this particle carried enough energy to power a small city for a fraction of a second. But the real shock came when scientists pointed their telescopes toward its origin. There was nothing there, no galaxy, no black hole, not even a flicker of radio waves or gamma rays, just empty space stretching endlessly in every direction. This wasn't just a missing source, it was a cosmic ghost. Most ultra-high-energy particles leave breadcrumbs, X-rays from a distant quasar, infrared glows from a colliding galaxy cluster, something to hint at their violent origins. But the high-res monocular event arrived without a single trace, as if it had been fired from a perfectly camouflaged cannon. Even stranger, its trajectory was pinned straight, defying expectations that galactic magnetic fields would warp its path beyond recognition. It pointed like an arrow into the void, taunting researchers with its unnatural precision. Theories crumble under scrutiny here. If the particle came from a nearby source, say, within our galactic neighborhood, why haven't we spotted any object capable of producing such insane energies? The Milky Way's known accelerators, like supernova remnants or pulsar wind nebulae, top out at mere fractions of this power. But if it traveled from intergalactic space, how did it dodge the energy-sapping collisions with cosmic microwave background photons that should have bled it dry over millions of light years? Some astronomers suggest we might be seeing the aftermath of a dark accelerator, an invisible astrophysical phenomenon like a rogue black hole or a decaying dark matter clump. Others wonder if magnetic fields far beyond our galaxy could be focusing these particles into beams so tight they mimic a single source, like sunlight through a magnifying glass. But without a visible counterpart to study, these ideas stay stuck in the realm of speculation. The high-res monocular event isn't just a scientific puzzle, it's a mirror held up to the limits of our cosmic vision. For all our telescopes and detectors, the universe still has corners where matter moves in ways we can't see, can't predict, and can't yet explain. Every time one of these phantom particles streaks through our atmosphere, it forces us to confront an unsettling truth. Space might be far stranger, far emptier, and far more mysterious than we ever dared to imagine. What if the most powerful cosmic accelerators in the universe are hiding in plain sight, not blazing with light, but cloaked in darkness? This is the spine-chilling premise behind the invisible accelerator theory, a radical idea gaining traction among astrophysicists desperate to explain ultra-high-energy cosmic rays. Rather than searching for bright, energetic objects like quasars or supernova, Some researchers now suspect the real culprits might be cosmic phantoms, structures so stealthy they leave no trace in our telescopes, yet pack enough brute force to launch particles with energies that dwarf anything produced in human-made colliders. Consider dormant quasars, the ghosts of once ferocious galactic engines. These supermassive black holes have exhausted their fuel supplies, their brilliant accretion disks gone dark after devouring all nearby matter. But some theorists suggest their magnetic fields might persist like cosmic scars, still coiled with enough tension to occasionally snap and fling stray particles to unbelievable speeds. Without fresh gas to light up their surroundings, these sleeping giants would be virtually undetectable until one of their cosmic bullets rips through Earth's atmosphere, betraying their presence. Then there's the dark matter angle, an explanation both elegant and maddeningly vague. We know this mysterious substance outweighs normal matter 5 to 1, clumping into vast halos around galaxies. While individual dark matter particles rarely interact with ordinary atoms, some models suggest dense knots of this invisible material could occasionally collide and annihilate, releasing bursts of energy capable of accelerating stray protons to ultra-high velocities. The catch: these events would leave no visible aftermath, just the faintest gravitational ripple and a handful of particles screaming across the cosmos. Perhaps the most unsettling possibility involves defects in spacetime itself. Cosmic strings, hypothetical cracks in the universe's fabric left over from the Big Bang, could theoretically vibrate like snapped guitar strings, releasing enough energy in a single tremor to power countless cosmic rays. If they exist, these strings would be thinner than an atom yet stretch across entire galaxies, invisible except for their gravitational fingerprints. When one twangs, the resulting shockwave might launch particles with such force they arrive at Earth looking like they've cheated physics itself. The frustrating beauty of these theories lies in their elusiveness. Invisible accelerators don't just challenge our understanding of cosmic rays, they force us to rethink how we study the universe. Traditional astronomy relies on capturing light across the electromagnetic spectrum. But if the cosmos' most energetic events leave no glow, we're essentially searching for footsteps in a pitch-black room. Every ultra-high-energy cosmic ray that matches no known source becomes a potential clue, a whisper from the universe's darkest corners hinting at forces we've yet to comprehend. Until we develop new ways to see the invisible, perhaps through gravitational wave observatories or neutrino detectors, these phantom accelerators will remain tantalizing maybes. They represent the ultimate cosmic hide and seek, where the hiders don't just conceal themselves but rewrite the rules of the game entirely. And with each mystery particle that arrives without explanation, the universe seems to be asking, how much of its violence happens where we can't even look? Deep in the frozen expanse of Siberia, where temperatures plunge to -60 degrees Celsius, a cosmic detective sits silently beneath the aurora-lit sky. The Yakutsk Extensive Air Shower Array, a network of sensors scattered across the permafrost, has been scanning the heavens for ultra-high-energy cosmic rays since the 1970s. And in 2008, it caught something unprecedented, a particle that didn't just break the rules, it tore up the rulebook entirely. This wasn't just another high-energy event, it was a cosmic outlier with an energy signature so bizarre, it left physicists questioning whether they'd witnessed a new kind of astrophysical phenomenon. What made this detection so extraordinary wasn't just its raw power, though at 150 exa-electronvolts, it certainly had plenty. It was the way it interacted with Earth's atmosphere. When ultra-high-energy cosmic rays collide with air molecules, they trigger cascades of secondary particles called extensive air showers, creating a predictable pattern scientists used to estimate their energy and composition. But the Yakutsk event produced a shower profile that defied all expectations. Instead of the typical proton-induced cascade, this one spread wider and deeper, as if something far heavier or far stranger had punched through the atmosphere. The data pointed to two equally puzzling possibilities. First, this might have been a nucleus from a heavy element like iron, accelerated to speeds no known cosmic engine should achieve. The problem: heavy nuclei are fragile over intergalactic distances. They should shatter like glass under the relentless bombardment of background radiation. For one to reach Earth intact at such energies would require either an impossibly near-by source or some unknown mechanism shielding it during its journey. The second possibility is even more radical. What if this wasn't ordinary matter at all? Some theorists suggest the shower pattern could hint at an exotic particle, something beyond the standard model of physics, carrying properties we've never observed. Imagine a particle that interacts with matter just enough to trigger a detectable shower, but not enough to lose energy the way protons or nuclei should. It's the cosmic equivalent of a ghost leaving footprints, visible effects without a traceable cause. For decades, Yakutsk's frozen sensors have stood as silent witnesses to the universe's most violent act. But this particular detection remains in a class of its own, an atmospheric fingerprint with no matching cosmic suspect. Whether it's revealing a new class of cosmic accelerators, challenging our understanding of particle physics, or hinting at something even more profound, one thing is certain: the Siberian skies hold secrets we're only beginning to unravel. And until we catch another like it, the Yakutsk Enigma will continue to whisper tantalizing questions from the edge of known science. When a cosmic ray smashes into Earth's atmosphere at nearly the speed of light, it doesn't arrive quietly. The collision triggers an explosive cascade, an atmospheric shower where the primary particle splinters into billions of secondary particles, creating a detectable footprint scientists use to trace its energy and identity. But sometimes these showers don't play by the rules. The ray we're examining didn't just break the mold, it shattered it, leaving a trail of clues that point to physics beyond our current understanding. Normally, ultra-high-energy protons create predictable showers. As they collide with air molecules, they spawn particle avalanches that spread outward in a pattern shaped by known physics, like a firework exploding in slow motion. The deeper the shower penetrates and the wider it fans out, the higher the initial energy. But this particular cosmic ray painted a different picture entirely. Its secondary particles rained down in a configuration so bizarre, it looked less like a firework and more like a shotgun blast fired upward from the ground. The anomaly lies in the shower's lateral spread. Standard models predict how far secondary particles should scatter based on the parent particle's energy and composition. Protons, being relatively light, produce narrow showers, while heavier atomic nuclei create broader ones. But this event spread wider than an iron nucleus should, while simultaneously plunging deeper into the atmosphere than any known particle ought to. It was as if the cosmic ray carried the mass of a lead atom, but the penetrating power of something infinitely smaller, a paradox that left researchers scrambling for explanations. One theory suggests we're seeing the handiwork of an entirely new class of particle, something outside the standard model that interacts with matter in ways we haven't yet codified. Imagine a particle that doesn't just collide with air molecules but skims them, transferring energy unevenly as it descends. This could explain the shower's strange hybrid profile, wide yet deep, as if the particle couldn't decide whether it was heavy or light. Another possibility: the culprit wasn't the particle itself, but the path it took to get here. Some researchers speculate magnetic fields between galaxies might have acted like cosmic lenses, subtly warping the particle's trajectory mid-flight. If it arrived at an angle or in an unexpected spin state, that could have distorted its atmospheric interaction, creating a shower that defies textbook predictions. But here's the catch: even the most sophisticated simulations can't fully replicate the observed data using known physics, the most unsettling implication. This might not be a fluke. Multiple detections from different observatories show similar anomaly showers that almost fit known models but deviate just enough to raise eyebrows. Together, they hint at a gap in our understanding of how matter behaves at energies far beyond anything we can recreate in labs. Every time one of these outliers streaks through our skies, it's like the universe is leaving breadcrumbs, tiny hints that the rulebook we've been using might need a rewrite. For now, the atmospheric shower puzzle remains unsolved, but with each new detection, we're gathering more pieces, and the picture they're forming is stranger than anyone expected. Whether it's new physics, hidden cosmic phenomena, or something even more extraordinary, one thing is clear: the universe isn't just playing by its own rules. It's changing the game entirely. In the rolling green hills of northern England, far from the high-tech detectors of modern observatories, a simple array of water tanks made a discovery that still baffles physicists today. The Haverah Park experiment, operational from 1967 to 1987, wasn't designed with flashy instruments or cutting-edge tech. Instead, it relied on something deceptively straightforward: large ponds of water that would light up with faint blue flashes when struck by the secondary particles of cosmic ray showers. And in the early 1970s, one particular event lit up those tanks like a cosmic fireworks display: an ultra-high-energy cosmic ray so powerful it defied explanation then and still doesn't fit neatly into our models today. What set the Haverah Park outlier apart wasn't just its energy, estimated around 200 exa-electron volts, putting it in the same league as the oh my god particle, but the way it interacted with Earth's atmosphere. Unlike most cosmic rays, which produce showers that fan out predictably as they descend, this one left a footprint that was strangely lopsided. The distribution of secondary particles hitting the water tanks suggested a shower that developed unevenly, as if the primary particle had somehow twisted or fragmented in midair. Modern simulations struggle to recreate this asymmetry, leaving researchers to wonder: was this a freak atmospheric disturbance or evidence of a particle with properties we've never accounted for? The mystery deepens when you compare Haverah Park's data to contemporary detections. Today's observatories, like the Pierre Auger Array or Telescope project, are exponentially more sensitive, yet they've never recorded another shower quite like this one. Some theorists argue that early experiments like Haverah Park might have suffered from calibration errors or environmental noise, but that explanation feels unsatisfying when you consider the sheer magnitude of the event. The tanks didn't just flicker, they erupted, registering a signal so clean and strong that interference seems unlikely. Others propose that the outlier might represent a rare class of cosmic ray that modern detectors, ironically, are too advanced to catch. Haverah Park's water tanks were uniquely sensitive to muons, heavy, penetrating particles that form a key component of air showers. If this particular cosmic ray produced an unusually high number of muons relative to other secondary particles, it could explain the anomaly. But here's the puzzle: no known astrophysical process should create a particle that generates such a muon-rich shower. Unless, of course, our understanding of high-energy particle interactions is missing a critical piece. The most compelling and unsettling theory, that the Haverah Park outlier was a fleeting glimpse of something transient and exotic, perhaps a microscopic black hole evaporating in the upper atmosphere, or a cosmic string snapping like an over-tensioned wire, releasing a burst of energy that faded before newer detectors could witness it. These ideas hover at the edge of theoretical physics, but they're not easily dismissed when faced with data that refuses to conform. 50 years later, the Haverah Park event remains a ghost in the cosmic ray catalogue, an enigma that refuses to be forgotten or explained. It's a reminder that sometimes the most profound mysteries don't come from the cutting-edge labs of today, but from the humble experiments of the past, patiently waiting for science to catch up. And until we find another like it, this outlier will continue to haunt the edges of our understanding, challenging us to question not just where cosmic rays come from, but what they truly are. The time-lagged mystery isn't just about a single cosmic ray, it's about the eerie silence that followed. Imagine witnessing a thunderclap so powerful it rattles windows for miles, only for the skies to go dead quiet afterward, leaving you wondering if you imagined the whole thing. That's the paradox haunting researchers studying this particular ultra-high-energy particle. Detected decades ago with instruments far cruder than today's observatories, it should have been the first of many. Yet nothing quite like it has been recorded since, as if the universe fired a warning shot and then vanished without a trace. One explanation points to the limitations of early detection systems. The instruments of the 20th century were like fishing nets with gaping holes capable of catching only the biggest, rarest fish while letting smaller ones slip through. Modern arrays like the Pierre Auger Observatory or Telescope project boast far finer resolution, theoretically making them better at spotting similar events. But here's the twist: if this cosmic ray was truly a fluke, an outlier of such rarity that even today's detectors haven't caught another, that raises an unsettling question. Are we dealing with something so extraordinary it defies statistical probability, like rolling a die and getting 1,000,000 sixes in a row? Then there's the possibility of transient cosmic events, phenomena so brief and violent they're over before we can blink. Picture a supermassive black hole belching out a single, hyper-accelerated particle during a rare moment of instability, or a neutron star's magnetic field snapping like a rubber band, launching a one-time cosmic projectile. These scenarios would explain why we haven't seen a repeat. The conditions needed to create such particles might be as fleeting as a lightning strike. But the most tantalizing theory involves what we can't see. If ultra-high-energy cosmic rays are being emitted by objects that don't glow, like dormant black holes or dark matter annihilations, we might lack the tools to connect the dots. Modern observatories excel at tracing particles back to visible sources, but what if the true accelerators leave no light signature? It's like hearing gunshots in the dark with no muzzle flash to reveal the shooter's location. The silence isn't just a scientific curiosity, it's a cosmic riddle wrapped in layers of uncertainty. Every year that passes without another detection forces us to confront the unnerving truth. The universe might be capable of producing phenomena so rare, so unpredictable, that catching them twice in a human lifetime could be a matter of sheer luck. Until then, the time-lagged mystery stands as a reminder. Some cosmic secrets aren't just hidden, they're once in an epoch whispers, daring us to listen more closely. Back in 1962, long before the era of massive digital arrays and space-based observatories, a cluster of simple particle detectors in the New Mexico desert recorded something extraordinary. Nestled among the scrub brush and volcanic rock of the aptly named Volcano Ranch experiment, a cosmic ray punched through Earth's atmosphere with an energy that rewrote scientific expectations: 100 exa-electronvolts, a number so staggering it forced physicists to reconsider the universe's most violent processes. This wasn't just another high-energy event. The Volcano Ranch detection marked a turning point, proof that nature could accelerate particles to energies far beyond anything human-made colliders could achieve. At the time, even the most powerful particle accelerators topped out at mere fractions of this energy. The discovery shattered assumptions, proving that somewhere out there, cosmic forces were at work that dwarfed humanity's technological prowess. But what made this detection truly remarkable was its timing. In an era when astrophysics still viewed cosmic rays as curiosities rather than cosmic messengers, the Volcano Ranch event became a Rosetta Stone for high-energy astrophysics. Researchers realized these weren't just random space particles. They were fingerprints of the universe's most extreme environments, carrying secrets about black holes, exploding stars, and perhaps even phenomena we hadn't yet imagined. The detectors themselves were almost comically simple by today's standards. An array of plastic scintillators spread across miles of desert, waiting to catch the faint flashes of light produced when cosmic rays slam into the atmosphere. Yet their data was unimpeachable. The shower pattern left by this event stretched wider and deeper than anything predicted by theory, suggesting either an unimaginably powerful source or a fundamental gap in our understanding of particle physics. Decades later, the Volcano Ranch ray still holds lessons. Its energy sits suspiciously close to what we now call the UHECR cutoff, the theoretical limit beyond which cosmic rays should be sapped of energy by cosmic microwave background radiation. That this particle arrived with such intensity hints that either it came from suspiciously nearby with no visible source to account for it, or our understanding of particle propagation through intergalactic space is incomplete. Modern simulations still struggle to explain its trajectory. The original data points to an arrival direction with no notable galaxies or black holes, just empty intergalactic space. Some researchers speculate it might have been focused toward us by intergalactic magnetic fields, like light bending through a lens, while others wonder if its true source has since dimmed or vanished entirely in the 60 years since its detection. The legacy of the Volcano Ranch event isn't just in the data it provided, but in the questions it forced scientists to ask. Before this detection, ultra-high-energy cosmic rays were theoretical curiosities. Afterward, they became unavoidable mysteries demanding answers. Every modern observatory, from the Pierre Auger array to the planned square-kilometer array, owes part of its existence to that unassuming desert experiment, proof that sometimes the most profound discoveries come not from cutting-edge labs, but from patient observers listening to the universe's quietest whispers. Those early desert experiments did more than just record cosmic rays, they changed how we see the universe. Before detectors like Volcano Ranch, ultra-high-energy particles were little more than theoretical possibilities, their existence debated in academic circles. But when those rudimentary scintillators lit up in the New Mexico desert, they didn't just capture data. They captured a paradigm shift. Scientists suddenly had proof that nature's particle accelerators dwarfed anything humanity could build, sparking a revolution in how we study high-energy astrophysics. What's astonishing isn't just what these experiments detected, but how they did it. Without satellite arrays or supercomputers, researchers relied on ingenuity and patience. Volcano Ranch's detectors were essentially buckets of water and plastic sheets spread across miles of arid terrain, waiting for the faintest flicker of light from particle collisions. Each detection required painstaking calibration, with scientists hiking through the desert to check equipment and manually record data. Yet from this analog persistence emerged discoveries that still shape modern cosmic ray research. The legacy of these early efforts lies in the questions they forced us to ask. When the Volcano Ranch team published their findings, they didn't just report an energy measurement, they inadvertently outlined the central mystery of ultra-high-energy cosmic rays that still puzzles us today. How could particles reach such velocities without visible sources? Why did they arrive from seemingly empty patches of sky? These weren't just technical curiosities. They were cracks in the foundation of astrophysics, hinting at cosmic processes we're only beginning to grasp. Modern observatories owe their design to these pioneering experiments. The sprawling grids of today's detector arrays, from the Pierre Auger Observatory to the Telescope Project, echo the decentralized layouts first tested in the 1960s. Even the concept of using Earth's atmosphere as a giant particle detector, a standard technique now, was refined through trial and error at sites like Volcano Ranch. Those early scientists didn't just collect data, they invented an entire methodology for studying the invisible universe. Yet perhaps the most profound lesson from this era is one of humility. For all our advanced technology, some cosmic rays detected half a century ago remain unexplained. The universe, it seems, reserved its hardest questions for future generations, using those first crude detectors as cosmic telegram machines delivering urgent messages we're still struggling to decode. As we peer deeper into the cosmos with increasingly sophisticated tools, those early desert experiments stand as a reminder. Sometimes the simplest instruments reveal the most profound truth. High above the frozen wastes of Antarctica, a balloon-borne detector named ANITA floated silently through the polar skies, hunting for whispers from the cosmos, but what it found would send shockwaves through the world of particle physics. Unlike ground-based observatories that catch cosmic rays slamming down from above, ANITA was designed to listen for something far stranger, ultra-high-energy particles screaming upward through the Earth itself. That shouldn't happen, at least not according to conventional physics. When high-energy particles collide with our planet's dense mass, they're supposed to disintegrate, their energy absorbed long before reaching the other side. Yet ANITA sensors picked up multiple events where cosmic rays seemed to defy this law, emerging from the ice with energies that left physicists scrambling for explanations. These weren't just flukes, they were potential cracks in the foundation of known physics. The most plausible explanation: ANITA might have spotted tau leptons, exotic particles produced when ultra-high-energy neutrinos interact deep inside the Earth. But here's the catch: ordinary neutrinos barely interact with matter at all. For one to collide with an atom and spawn a tau lepton capable of punching through thousands of miles of rock would require energy so extreme they'd dwarf even the most powerful cosmic rays we've seen. It's like expecting a whisper to shatter a brick wall. The implications sent theorists down a rabbit hole of possibilities. Could these detections hint at sterile neutrinos, hypothetical particles that bypass normal matter entirely, only revealing themselves through rare, explosive interactions? Or are we seeing evidence of something even more exotic, like magnetic monopoles or particles from extra dimensions? The math gets dizzying, but the core mystery remains. If these events are real, they point to physics beyond the standard model, a tantalizing glimpse of the universe's hidden rulebook. Yet skepticism lingers. Critics argue that ANITA anomalies might be glitches, cosmic noise masquerading as breakthroughs. After all, no other detector has replicated these upward-moving events with certainty. But if ANITA data holds up, it could rewrite our understanding of how particles interact with matter, revealing cosmic accelerators far more powerful than anything we've dreamed of. For now, these Antarctic anomalies hover in scientific limbo, too strange to ignore, too rare to confirm. They're cosmic riddles wrapped in ice, waiting for the next experiment to crack them open. Buried beneath 2 miles of Antarctic ice, the continent itself becomes a scientific instrument, one that ANITA turns into the largest neutrino detector on Earth. Unlike traditional observatories scanning downward from space or mountain peaks, this balloon-borne experiment peers upward, using the ice sheet as a colossal filter. When ultra-high-energy particles slice through the planet from the northern hemisphere, most fizzle out long before reaching the southern ice, but a rare few possessing impossible energies leave behind flashes of radio waves as they emerge, detectable only by ANITA suspended antennas drifting 37 kilometers above the surface. It's cosmic detective work at its most ingenious, using Earth as a sieve to catch the universe's most elusive particles. The magic lies in what gets filtered out. Typical cosmic rays, protons or atomic nuclei, never make it through. They're absorbed within kilometers of entering the atmosphere. Even most neutrinos, famed for their ghostly ability to pass through matter, rarely interact with the ice enough to leave a trace. But ANITA anomalous events behave differently. They produce radio signals consistent with particles erupting from below, like geysers of energy, blasting upward through the ice after traversing the entire planet. The math here is merciless. For a neutrino to interact so violently inside Earth that it spawns a particle detectable on the other side, it would need energies exceeding 100 exaelectron volts, orders of magnitude beyond what conventional astrophysical sources should produce. This forces physicists down 2 thorny paths. Either we're witnessing neutrinos born in cosmic explosions so cataclysmic they rewrite energy limits, or these aren't neutrinos at all. Some theorists suggest ANITA might have glimpsed speculative particles like the sterile neutrino. a hypothetical variant that interacts solely through gravity and weak nuclear forces. These shadowy particles could theoretically accumulate in Earth's core over eons before annihilating in bursts energetic enough to mimic cosmic rays. Others wonder if we're seeing the handiwork of magnetic monopoles, long theorized single-pole magnets that could tunnel through matter with minimal resistance, depositing energy in sporadic bursts. Even the laws of relativity get dragged into the debate. At energies this extreme, particles might experience time differently due to relativistic effects, effectively seeing Earth's crust as thinner than it appears to us. It's a mind-bending concept, a particle moving so close to light speed that its compressed perception of space-time allows it to traverse the planet before decaying. But this too strains credibility, requiring energy so high they border on the absurd. The true headache comes from conflicting data. While ANITA detections align with some neutrino models, they wildly contradict results from IceCube, the massive neutrino observatory buried in the same Antarctic ice. IceCube should have spotted corroborating signals from these events, yet its sensors remain stubbornly silent. This discrepancy has researchers questioning everything. Are ANITA instruments catching cosmic rays masquerading as upward-moving particles? Is there an unknown atmospheric phenomenon mimicking neutrino interactions? Almost thrillingly, are we seeing the first cracks in the Standard Model's foundation? For now, the Antarctic ice guards its secrets. With ANITA final flight completed and no successor mission yet funded, these anomalies linger in scientific limbo, too extraordinary to dismiss, too rare to confirm. They stand as a testament to the universe's penchant for defiance, reminding us that even our boldest theories are just sketches of a cosmos that always finds ways to surprise. Until another detector picks up the trail, these upward shooting particles remain both a tantalizing clue and a frustrating dead end, a cosmic whisper just loud enough to hear but too faint to decipher. Just when scientists thought they had mapped the cosmos' most energetic mysteries, the universe threw them another curveball, one that came from the same patch of sky as before, but with twice the intrigue. The Telescope Array project, already famous for spotting the first ultra-high-energy cosmic ray hotspot near Ursa Major, recently expanded its reach with 4 times as many detectors. Dubbed TAX-4, this upgraded network didn't just confirm the original hotspot, it found a second one, blazing from the same general direction but offset by a tantalizing margin. The implications: we might be looking at fragments of something far grander, a hidden cosmic structure weaving through the void, its presence betrayed only by the particles it slings our way. Both hotspots share eerie similarities. Each spans roughly 20 degrees of sky, a cosmic bullseye where ultra-high energy rays cluster with statistical significance too high to dismiss as coincidence. Yet the new hotspot sits slightly askew, like a shadow of the first, close enough to suggest a connection, but distant enough to raise questions. Is this a double-barreled cosmic accelerator, firing particles from 2 distinct nodes? Or are we seeing the distorted imprint of a single massive object, its emissions warped by intergalactic magnetic fields into overlapping but misaligned patterns? Theories spiral in fascinating directions. One compelling idea posits that both hotspots trace back to a supergalactic structure, an invisible filament of dark matter or a congregated swarm of active galaxies too faint to spot from Earth. Picture a cosmic freeway where particles surf magnetic shockwaves along these hidden thoroughfares, their paths funneled toward us like water through a hose. Alternatively, the twin hotspots might mark the edges of a colossal intergalactic shock front, where colliding galaxy clusters generate turbulence powerful enough to accelerate particles to unfathomable speeds. Yet the puzzle deepens when you compare their energy profiles. The original hotspot's rays pack slightly more punch on average, hinting that whatever's producing them might be closer or more ferocious. The TAX-4 hotspot's particles, while still mind-bendingly energetic, skew toward lower energies, as if they've traveled farther or been filtered through thicker cosmic debris. It's the difference between a gunshot heard up close and one muffled by distance, leaving researchers to wonder, are we hearing two distinct cosmic explosions or echoes of the same event bouncing off different corners of the universe? The most electrifying possibility, these hotspots aren't anomalies at all, but signposts in a much larger pattern. If future expansions of the telescope array uncover more clustered rays in this celestial neighborhood, we might be staring at the outline of a cosmic web, node a nexus where dark matter and galaxies converge, their combined gravitational and magnetic fields acting as a particle accelerator on intergalactic scales. It's a humbling thought. What we've been calling hotspots could be mere pixels in a universe-spanning portrait, one we're only beginning to bring into focus. For now, the Tax-4 hotspot remains a riddle wrapped in a mystery, a cosmic whisper that grew louder when we learned to listen better. With every upgrade to our detectors, the universe seems to reveal another layer of its complexity, daring us to dig deeper. And as these twin hotspots pulse silently in the darkness, they challenge us to rethink not just where cosmic rays come from, but how the hidden architecture of the cosmos itself might be shaping their journey. The twin hotspots spotted by the telescope array aren't just random blips on the cosmic radar. They might be revealing the hidden scaffolding of the universe itself. When astronomers trace their positions against the known large-scale structure of our cosmic neighborhood, an intriguing pattern emerges. Both align loosely with the fringes of the local supercluster, a vast web of galaxies stretching hundreds of millions of light years, with the Milky Way clinging to its outer edges like a barnacle on a ship's hull. This supercluster isn't just a random gathering of stars. It's threaded with colossal filaments of dark matter and gas, invisible rivers of gravity that could be channeling cosmic rays toward us like water through a canyon. But here's where it gets speculative. The local supercluster's filaments are notoriously difficult to map. Unlike galaxies which glow with starlight, these cosmic tendrils are made mostly of dark matter and sparse hydrogen material that emits no light and betrays its presence only through subtle gravitational tugs on surrounding galaxies. If the hotspots are connected to these structures, they could be signposts pointing to regions where intergalactic magnetic fields are unusually strong, acting like cosmic particle slingshots. Imagine a galactic freeway where magnetic shockwaves accelerate protons to near light speeds, then fling them across the void with pinpoint accuracy toward Earth. The challenge: correlation doesn't equal causation. While the hotspot's rough alignment with the supercluster is tantalizing, it's far from definitive proof. Alternative explanations abound. Perhaps we're seeing the aftermath of a long-ago galaxy collision, where shockwaves from the impact created temporary particle accelerators now fading into oblivion. Or maybe the local supercluster's magnetic fields are warping cosmic ray paths in ways we can't yet simulate, creating phantom hotspots that don't reflect true source locations. One provocative theory suggests these filaments aren't just passive conduits but active cosmic accelerators. In regions where filaments intersect, the gravitational chaos could generate turbulence powerful enough to energize particles to extreme velocities, like a natural version of the Large Hadron Collider, but operating on scales we can barely comprehend. If true, it would mean the universe's largest structures aren't just celestial backdrops. They're dynamic engines capable of generating the most energetic particles we've ever seen. Yet for all the excitement, the evidence remains frustratingly circumstantial. Without precise source identification or a better understanding of how magnetic fields sculpt cosmic ray trajectories across millions of light years, the supercluster connection stays in the realm of educated guesswork. It's like trying to reconstruct a thunderstorm by studying the raindrops that hit your roof. You know they came from somewhere up there, but the exact mechanics of the storm remain shrouded in mystery. What makes this debate so electrifying isn't just the science, it's the sheer scale of the implications. If these hotspots truly trace the bones of the cosmic web, they could offer humanity its first indirect map of the universe's hidden architecture. Every ultra-high-energy particle becomes a cosmic messenger, carrying encrypted notes about the invisible forces that shape existence itself. Until we crack that code, these twin hotspots will keep burning in the darkness, silent beacons from the universe's most secret blueprints. Nestled in the forested hills of Karlsruhe, Germany, the Cascade Grand experiment spent years quietly rewriting the cosmic ray playbook. Unlike detectors that simply measure energy, this sprawling array of scintillators and muon trackers had a sharper focus. It could dissect air showers to reveal not just how powerful incoming particles were, but what they were made of. And when it turned its gaze to ultra-high-energy cosmic rays, the results shattered expectations. Instead of lightweight protons dominating the highest energies as predicted, Cascade Grand found something far stranger. Heavy nuclei like iron screaming through the atmosphere at velocities that should have been impossible. This wasn't just an oddity, it was a fundamental challenge to how we think cosmic accelerators work. Conventional models suggest heavy atomic nuclei are fragile travelers. At extreme energies, they should shatter like glass during their journey, broken apart by collisions with the sparse photons permeating intergalactic space. Protons, being simpler and more stable, were thought to be the only particles capable of surviving long enough to reach Earth with such mind-bending energy intact. Yet Cascade Grand's data painted a different picture. A significant fraction of ultra-high-energy cosmic rays arriving with signatures matching heavy elements, as if nature had somehow forged cosmic cannonballs out of lead and launched them across the universe unscathed. The implications ripple through astrophysics. If heavy nuclei truly dominate at the highest energies, it forces a radical rethink of cosmic accelerators. Black hole jets and supernova remnants, long favored as particle powerhouses, might need revision, since their mechanisms are typically tuned for proton acceleration. Some theorists now speculate we're seeing the handiwork of rarer, more violent phenomena, perhaps colliding galaxy clusters where shockwaves in million-degree plasma could forge and fling heavy elements to outrageous speeds. Others wonder if magnetic fields in galactic halos might act like cosmic centrifuges, preferentially slinging heavier elements outward while lighter particles get trapped. Complicating matters further is the question of distance. Heavy nuclei have more electric charge than protons, making them far more susceptible to deflection by interstellar and intergalactic magnetic fields. That means their arrival directions shouldn't point back to their sources. They'd be scrambled beyond recognition during their journey. Yet when researchers try to trace these particles backward, some seem to cluster in suspiciously tight groupings, as if they've somehow resisted the magnetic chaos. It's like tracking a bullet through a hurricane and finding it landed precisely where it was aimed. The Cascade Grand puzzle doesn't just challenge individual theories, it exposes gaps in our understanding of particle propagation itself. Are we underestimating the resilience of heavy nuclei, misjudging the structure of galactic magnetic fields, or overlooking entirely new physics that lets certain particles cheat the cosmic friction that should slow them down? With each new detection, the mystery deepens, leaving physicists to grapple with a universe that seems determined to defy even its own rules. What makes these heavy cosmic bullets so captivating isn't just their existence, it's what they imply about the hidden engines powering them. If nature can forge and fling atoms of iron across the cosmos with energies no human collider could ever match, then somewhere out there, lurking in the darkness, are forces we've barely begun to comprehend. Until we crack this puzzle, every heavy nucleus that streaks through our atmosphere carries not just energy, but a silent challenge. Look harder, think deeper. The cosmos has more to teach us than we've dared to imagine. There's something deeply unsettling about heavy nuclei arriving at ultra-high-energy cosmic ray speeds, like finding an anvil floating effortlessly in midair. Physics tells us these atomic behemoths, packed with protons and neutrons, shouldn't survive the brutal journey through intergalactic space intact when accelerated to such extreme velocities. The cosmic microwave background, that faint echo of the Big Bang permeating every cubic inch of the universe, should act like a sandblaster, chipping away at their structure with countless high-energy photon collisions over millions of light years. Protons might tough it out, but heavy nuclei like iron, they're supposed to shatter long before reaching Earth, their components scattered across the void like debris from a high-speed collision. Yet detectors like Cascade Grand keep catching them red-handed. These rogue particles carry all the hallmarks of heavy elements: wider atmospheric showers, more secondary muons, and they're arriving with energies that defy logic. It's as if the universe has discovered a way to wrap fragile glass in armor plating and fire it through a minefield unscathed. The implications are staggering. Either our understanding of particle propagation through space is fundamentally flawed, or there are cosmic accelerators out there operating on principles we've never imagined. Take the case of iron nuclei. At the energies we're observing, each collision with a microwave background photon packs enough punch to knock loose individual nucleons, protons, and neutrons from the nucleus. Over intergalactic distances, this photodisintegration should reduce even the sturdiest iron nucleus to a spray of lighter particles long before it reaches our detectors. The fact that some survive suggests they either came from suspiciously nearby with no visible sources to explain their acceleration, or found some way to cheat the system. Some theorists propose these nuclei might be riding cosmic shortcuts, folded space-time pathways where they bypass the usual photon gauntlet entirely. Others suggest they could be products of nuclear restoration, where shattered fragments somehow reassemble mid-journey through exotic quantum effects. The plot thickens when you consider acceleration mechanisms. Traditional cosmic ray sources like supernova remnants excel at boosting protons but struggle with heavy elements. The shock waves simply don't pack enough sustained force to push something as massive as an iron nucleus to these extreme velocities. This has physicists scrambling to propose more violent alternatives, perhaps mergers of neutron stars, already known to forge heavy elements, could generate additional shockwaves capable of cosmic ray acceleration. Or maybe active galactic nuclei contain hidden heavy ion modes in their jets, preferentially accelerating metals over hydrogen. Even our detection methods are being questioned. Some researchers argue that what we interpret as heavy nuclei might instead be tight clusters of protons arriving in near-perfect synchronization, an atmospheric mirage created by bizarre magnetic focusing effects. Others counter that no known magnetic phenomenon could orchestrate such precise coordination across millions of light years. The debate cuts to the core of how we study cosmic rays. If we can't even agree on what's hitting us, how can we hope to understand where it's coming from? This paradox forces us to confront the limits of our cosmic knowledge. Every heavy nucleus that shouldn't exist but does is a reminder that the universe's playbook contains chapters we haven't been given yet. Whether it's revealing unknown astrophysical processes, exposing flaws in our propagation models, or hinting at entirely new physics, these impossible particles are cosmic messengers delivering the same urgent memo. There's more to space than meets the eye or the detector. The Chico's array should have been the perfect cosmic ray detective. Nestled in the mountains of Southern California, this network of detectors was designed to catch ultra-high-energy particles with precision. Its location carefully chosen to minimize interference from city lights and radio noise. But when it started logging data in the early 2000s, scientists quickly realized they weren't just mapping cosmic rays, they were staring at a cosmic conspiracy. The particles arriving with the highest energies refused to point back to any known sources in our galaxy. No supernova remnants, no pulsar wind nebulae, not even the Milky Way's bustling center. Instead, they sprayed across the sky in a pattern so random, it seemed the universe was playing a prank. Here's the puzzle. If these cosmic rays came from outside our galaxy, their path should be warped by the Milky Way's magnetic field, twisted like spaghetti in a whirlpool, making their original directions untraceable. Yet some showed up with such staggering energy that they should have resisted significant deflection, their trajectories staying true enough to hint at distant quasars or colliding galaxy clusters. But Chico's found no such patterns. The highest energy arrivals weren't just misaligned, they were anti-correlated with the galaxy's structure, as if deliberately avoiding known astrophysical landmarks. One theory blames local magnetic fields, not just the broad sweep of the Milky Way's magnetism, but smaller, messier structures closer to home. Imagine Earth floating inside a cosmic funhouse mirror, where nearby gas clouds and stellar debris create magnetic knots that scramble incoming particle paths beyond recognition. These tangled fields could twist trajectories so severely that even rays from obvious sources end up appearing to arrive from nowhere. But there's a catch. If local fields are distorting paths this dramatically, why don't all cosmic rays show similar chaos? Lower energy particles, which should be more susceptible to magnetic interference, often trace back to galactic sources just fine. It's only the ultra-high energy outliers that seem utterly lost. This selectivity has physicists questioning whether we're dealing with a magnetic mystery or something far stranger. Alternative explanations flirt with the edge of known physics. Could these rays be emerging from dark cosmic accelerators, objects that don't glow in any wavelength we can detect? Or perhaps they're the fallout of rare particle decays in the Milky Way's halo, their origins obscured not by magnetism but by the sheer strangeness of their birth. The most radical suggestion that these particles aren't traveling in straight lines at all, but are somehow remembering earlier paths through quantum entanglement or extra-dimensional shortcuts. Chico's mystery rays force a humbling admission. For all our maps of the galaxy's magnetic fields, we might still be missing crucial details, like trying to predict a lightning strike while ignoring the shape of the landscape. Our models could be overlooking hidden pockets of magnetic turbulence, invisible whirlpools that steal the truth from incoming cosmic messengers. Until we can peer deeper into the magnetic maze surrounding Earth, these particles will keep their secrets, arriving like anonymous letters with the return address scratched out. The real lesson here isn't just about cosmic rays, it's about the universe's knack for deception. Sometimes the biggest mysteries aren't found in distant galaxies or exotic particles, but in the quiet distortions of the space right next door. And until we untangle those knots, the Chico's detections will stand as a reminder. Even when the cosmos sends us signals, there's no guarantee we'll understand the way they've been bent along the way. Galactic and extragalactic space isn't just empty, it's threaded with invisible magnetic fields, a labyrinth of force lines twisting and turning like cosmic spider silk. These fields might seem insignificant compared to the raw power of black holes or supernova, but when it comes to ultra-high-energy cosmic rays, they're the ultimate illusionist. A particle blasting toward Earth at nearly the speed of light doesn't travel in a straight line. It gets yanked, spun, and rerouted by these magnetic currents, turning what should be a clear path back to its origin into a tangled mess. Take the Milky Way's magnetic field as a starting point. It's not uniform like a bar magnet's, it's a chaotic web with strengths varying wildly between regions. Near the galactic core, fields are intense enough to bend even the highest energy cosmic rays, while in the spiral arms they're weaker but no less complex. Imagine throwing a handful of iron filings into a storm. That's roughly what happens to a cosmic ray's trajectory as it weaves through these fields. By the time it reaches us, its original direction could be off by tens of degrees, leaving astronomers staring at a cosmic dead end. But the real fun begins beyond our galaxy. Intergalactic space isn't the perfect vacuum we once thought. It's laced with diffuse magnetic fields, remnants of ancient galaxy collisions or jets from long-dead quasars. These fields are far weaker than those inside galaxies, but over millions of light years, their effect adds up. A proton arriving from a distant active galaxy might start its journey pointed straight at Earth, only to be nudged subtly at first, then more drastically, until its path resembles a pinball ricocheting through a maze. The worst part, we can't even map these fields precisely. Unlike stars or gas clouds, magnetic fields don't emit light. We infer their presence indirectly by observing how they polarize starlight or bend radio waves. This means our models of cosmic ray deflection are built on educated guesses, with error bars wide enough to drive a galaxy through. When a high-energy particle arrives from an apparently empty patch of sky, we're left wondering, is there truly nothing there, or have the fields tricked us into looking the wrong way? Some theorists argue that the highest energy cosmic rays might hold a clue. Particles with extreme rigidity resisting magnetic deflection like a freight train plowing through fog should theoretically point closer to their true sources. Yet even these occasionally arrive from baffling directions, hinting that somewhere in the cosmic background there are magnetic structures we've yet to account for. Could there be vast, unrecognized magnetic filaments spanning galaxy clusters, or perhaps temporary magnetic mirrors formed by shock waves in intergalactic plasma, bending particle paths in ways our simulations don't yet capture? The irony is delicious. The same forces that make cosmic rays detectable also obscure their origins. Every ultra-high-energy particle that streaks through our atmosphere is both a message and a cipher, scrambled by the universe's own encryption. Until we crack the magnetic code or develop new ways to peer through the distortion, these messengers will keep arriving like letters with half the words smudged out, hinting at wonders just beyond our grasp. Floating 20 miles above the Pacific Ocean, a high-altitude balloon carrying one of the most sensitive cosmic ray detectors ever built was supposed to survey the night sky for faint flashes of ultraviolet light, the telltale signatures of ultra-high-energy particles slamming into Earth's atmosphere. The Extreme Universe Space Observatory on a super-pressure balloon, or USO-SPB, wasn't just another science experiment. It was a technological marvel designed to peer deeper into cosmic ray origins than ever before. But what it found during its 2017 mission sent shockwaves through astrophysics particles so energetic, their existence hints at accelerators operating not just beyond our galaxy, but possibly beyond the entire local universe. This wasn't just a routine detection. The USO-SPB caught several ultra-high-energy cosmic rays UHECR with energies exceeding 100 exa-electronvolts, so powerful that they punched through layers of atmosphere with barely any resistance. But here's the twist. When researchers traced their potential origins backward, they hit a cosmic wall. The particles appeared to arrive from regions of space so distant, their light hasn't had time to reach us yet. In other words, if these cosmic rays truly came from where their trajectories suggest, they'd have to originate from beyond the cosmological horizon, the observable edge of our universe. The implications boggle the mind. According to our current understanding, nothing should be able to traverse such vast intergalactic distances without losing energy to interactions with the cosmic microwave background. Yet these particles seem to have done the impossible, crossing unfathomable voids without the expected energy drain. It's like finding a bullet that traveled halfway across the planet without slowing down, then realizing the gun that fired it hasn't even been invented yet. One theory points to flaws in our cosmic distance ladder, perhaps errors in how we calculate the universe's expansion or map large-scale structures, but the more tantalizing possibility. These particles might be evidence of physics operating beyond the standard cosmological model. Some theorists suggest they could be relics from the inflationary epoch, leftover energy from the universe's violent birth, preserved in particles that have been wandering the cosmos since the first fraction of a second after the Big Bang. Others speculate about top-down mechanisms, where the decay of hypothetical supermassive particles from the early universe releases ultra-high-energy descendants billions of years later. Then there's the balloon mission itself, a feat of engineering as daring as its discoveries. UHECR's detectors, suspended beneath a stadium-sized balloon, had to distinguish between cosmic rays and atmospheric noise while drifting uncontrollably in the stratosphere. Each detection required pinpoint timing to separate real signals from false alarms caused by lightning, meteors, or even passing airplanes. The fact that these anomalies stood out so clearly against such a chaotic background makes them impossible to dismiss as mere instrument glitches. Yet skepticism remains. Without a second mission to confirm the findings, UHECR's flight was cut short due to balloon issues. The data exists in scientific limbo. Are these truly particles from beyond the horizon, or is there a more mundane explanation? Could intergalactic magnetic fields, still poorly understood, be warping particle paths in ways that fool our reconstructions? Or might these cosmic rays be secondary products, debris from even higher energy particles that collided with unseen dark matter halos, creating energetic shrapnel that only appears to come from nowhere? What makes the UHECR anomaly so electrifying isn't just the mystery of its origins, but what it reveals about the limits of our cosmic vision. Every ultra-high-energy particle that defies explanation is a reminder that the universe's greatest wonders might lie not just in the stars we see, but in the darkness beyond what we can observe. Until another detector takes to the skies to chase these ghosts, they'll hover at the edge of discovery, proof that sometimes the most profound secrets come from places we can't even look. The notion that ultra-high-energy cosmic rays could travel billions of light-years without losing energy isn't just a fringe idea. It's a direct challenge to one of astrophysics' most robust predictions, the UHECR cutoff. Named after Grison, Zatsepin, and Kuzmin, this theoretical limit states that any proton with energy above 5 × 10⁻¹9 electron volts should collide relentlessly with photons from the cosmic microwave background, the faint afterglow of the Big Bang. Each collision would sap its energy like a marathon runner hitting wall after wall until it drops below the threshold. Yet a handful of cosmic rays gleefully ignore this rule, arriving with energies that mock the very equations meant to contain them. So how might they cheat the system? One possibility is that these particles aren't traveling the full distance we assume. If their sources lurk surprisingly close, within 100 million light-years or so, they might slip through before the cosmic microwave background can wear them down. But here's the catch. Our most detailed sky surveys show no obvious accelerators in this neighborhood capable of such violence. No quasars, no colliding galaxy clusters, not even a whisper of gamma-ray bursts. It's like hearing gunshots in your backyard but finding no shooter. Another explanation invokes the quirks of particle physics itself. At energies this extreme, protons might morph into exotic states, briefly becoming particles called prions or quark matter that interact differently with the cosmic microwave background. Picture a shape-shifter dodging obstacles by changing form. Mid-stride, these theoretical particles could skirt the usual energy loss mechanisms, only reverting to normal protons as they near Earth. The math here is speculative, but the allure is undeniable. It hints at physics beyond the standard model, lurking just beyond our current experiment's reach. Then there's the intergalactic medium's hidden structure. We often treat space as a uniform void, but what if it's riddled with low-density bubbles where the cosmic microwave background is weaker? A particle threading this cosmic maze might find rare paths where collisions are sparse, like a messenger sprinting through a battlefield during lulls in gunfire. Supporting this idea are observations of large-scale cosmic voids, regions hundreds of millions of light-years across with far fewer galaxies and gas. If ultra-high-energy cosmic rays are funneled through these emptier corridors, they could emerge relatively unscathed. The wildest hypothesis, these particles aren't traveling linearly at all. Some models suggest that ultra-high-energy protons might interact with hypothetical quantum foam, the frothy texture of spacetime at microscopic scales, allowing them to tunnel through high-interaction regions without losing energy. Others speculate about cosmic strings or other space-time defects acting as particle highways, bending the usual rules of propagation. These ideas flirt with the edges of theoretical physics, but when faced with observations that defy conventional wisdom, even fringe theories deserve a hearing. What makes the intergalactic traveler hypothesis so compelling isn't just its audacity, but what it reveals about our cosmic blind spots. Every time a particle smashes through the UHECR cutoff, it forces us to reconsider what we think we know about the universe's fabric. Whether through unseen astrophysical loopholes, new particle behaviors, or hidden structures in the void, these cosmic rays are more than anomalies. They're potential keys to unlocking physics we've yet to imagine. And until we catch one red-handed tracing its journey from source to detector, the mystery will keep taunting us. How far can a single particle really go? From the oh my god particle's jaw-dropping energy to the eerie silence of the time-lagged mystery, these 30 cosmic rays aren't just scientific oddities, they're cosmic revolutionaries. Each one defies explanation in its own way, whether by arriving from voids of nothingness, laughing off the UHECR cutoff, or clustering in hotspots that point to hidden celestial architectures. Together, they form a constellation of enigmas, challenging everything we thought we knew about particle acceleration, magnetic fields, and the universe's most violent engines. What makes these discoveries so thrilling isn't just their individual strangeness, it's the collective story they tell. Like pieces of a puzzle we're only beginning to assemble, they hint at a cosmos far wilder than our textbooks describe. Some could be cosmic SOS signals from dying stars, while others might be the fallout of dark matter annihilations or the tremors of space-time itself. The common thread, they all push astrophysics to its limits, forcing us to rewrite theories, question assumptions, and stare into the abyss of our own ignorance. Consider the implications. If nature can fling particles with energies 1 billion times beyond our most powerful colliders, what else is it capable of? Could there be entire classes of cosmic accelerators invisible, undetectable, lurking just beyond our perception? Are we glimpsing the edges of new physics where particles behave in ways the standard model can't explain? Every unanswered question is an invitation to explore further, dig deeper, and rethink what's possible. This isn't just about solving mysteries, it's about embracing them. The universe isn't obligated to make sense to us, and that's what makes science so exhilarating. Each cosmic ray that crashes through our models is a reminder. The cosmos is stranger, more inventive, and more defiant than we've dared to imagine. So what do you think is out there? A hidden network of dark matter particle cannons, rogue black holes slinging matter across the void, or something even more extraordinary? Drop your wildest theories in the comments, because in a universe this bizarre, no idea is too far-fetched. And if you're hungry for more cosmic enigmas, hit subscribe. The universe isn't done surprising us yet, and neither are we. The next revelation could be just one detection away, and you won't want to miss it.